Hello everyone, warm greetings. My name is Vyas. I'm pleased to be a part of the 13th International Conference on Database Management Systems. And the title of my presentation is Study of Performance and Consistency Trade-off in Cassandra. The first slide is about the overview of the presentation. The topics that I'll be discussing are mentioned on this slide. I'll start with the motivation. Consistency is an important factor for any database management system. Cassandra, which is a focus of our work here, is a NoSQL database, and as we will see further, it provides eventual consistency. But any user would want that the data on which he or she is working on is strongly consistent. Therefore, a need to find a proper consistency setting arises such that it provides low latency, good throughput, and good performance. Cassandra provides tunable consistency, which means that the consistency can be modified, and we take advantage of this feature and make our system strong. Understanding the trade-off between consistency and delay is crucial, and the primary focus is to investigate how different combinations of consistency affect the performance of the system. And using the parameters such as consistency, latency, throughput, experiments are performed and the results are recorded. And the results and analysis will be specific to our setup. So to allow any other developer to predict these values for their unique setups, generalized regression equations are formed and extracted from the data that we have recorded through our experiments, such that the values of the parameters can be predicted beforehand for any setup. Coming to the problem statement, the problem that we are addressing here is to make an eventually consistent system strongly consistent. Along with taking the delays, throughput, and performance into consideration, we don't want to miss the other aspects of performance while only focusing on consistency. For that, the behavior of the database has to be tracked. Here, we are considering various percentages of read and write workloads, different level of consistency, and with a varying number of threads, the experiments will be performed. And various workload runs are executed and the results are measured. We want the developers to forecast the parameters for their unique setup, and for that, a benchmarking approach needs to be developed such that the results and equations are extracted, which can then be used for predictive analysis. Starting from the background, NoSQL databases are non-relational databases that store data differently than relational database. NoSQL systems provide flexible schemas and they can scale easily with larger amounts of data. Nowadays, the data that applications store and query has increased. Data of various formats are seen nowadays in IoT devices such as smartwatches, smart TVs, and home assistants. So the data comes in all different shapes and sizes. It can be structured, semi-structured, unstructured, and therefore defining schema for such a data becomes nearly impossible. Therefore, NoSQL databases have gained popularity and it allows developers to store huge amounts of unstructured data, giving them a lot of flexibility. It has high availability and they are scalable. And because of the complex functionalities that NoSQL databases provide, they have to compromise with the consistency and provides eventual consistency, which is the concern that we are trying to improve. Cassandra database. It is a type of column-oriented NoSQL database. It can work with massive amounts of different kinds of data. And the main features that the database provides are fast writes, high performance, and flexible data storage. Cassandra provides a familiar interface, which is known as Cassandra Query Language, similar to the SQL that we have for relational model. And it offers an abstraction layer that hides the implementation details, and we can work with the database using CQL. Talking about the basic structure, the data in Cassandra is kept in key spaces, which is also similar to the databases that we have in relational model. So the key space have a group of column families similar to tables, and then the column families contains row which are made up of columns. Replication in database is supported by Cassandra to ensure availability in the event of failure or other predefined activity. The term replication factor refers to the total number of replicas in the cluster where data is replicated. Cassandra keeps replicas on several different nodes to ensure fault tolerance and reliability. If the data is replicated and if one node fails, then we would have the same data replicated on other nodes, which will make the system fault tolerant and reliable for a user. Replication factor of 1 means that each row in the cluster has only one copy. A replication factor of 2 means that there are 2 copies of a single data in the cluster, and similarly. Replication factor can be specified at the time of the key space generation. Consistency. So whenever a read or write operation is performed, then the minimum number of Cassandra nodes that needs to acknowledge that operation before it may be declared as successful is known as the consistency level. And different databases or key spaces have different consistency level allocated to them. The consistency option of 1 indicates that for any read or write operation to succeed, at least one node has to react. Similarly, for a consistency level of 2, 2 nodes in the cluster needs to react for that operation to be successful. In CQL, which is provided by Cassandra, we can simply use a consistency command and set the consistency setting for that session. Therefore, the consistency levels that we have here are 1, quorum, and all. So if I have a cluster of 3 nodes and I set a consistency level of 1, then it means that at least one node needs to react. Quorum means majority of nodes. And for an operation to be successful, a quorum of nodes has to respond to make the operation successful. So for example, if I have a cluster of 3 nodes, then quorum becomes 2 using this equation. And if I have a cluster of 100 nodes, then the quorum nodes becomes 51. So basically it's a majority of nodes. And similarly for all nodes. To get strong data consistency, the equation has to be followed. The sum of nodes returned and read has to be greater than the replication factor. And if this equation is satisfied, then we can say that the system provides strong consistency. YCSB Benchmark. YCSB is an abbreviation of Yahoo Cloud Serving Benchmark. It is a program suite for evaluation and comparison of the performance of different NoSQL databases. Majorly, it has 2 components. It has a workload generator client that loads and runs the workload, and a set of basic standard workloads that cover various aspects of the performance. And by default, YCSB provides 5 workloads, namely A, B, C, D, and E. And in our experiment, we will be using workload A, parameterized to execute only write operations, and workload C, which is 100% read operations. The software or tools that are required for the execution of our experiments are mentioned on this slide. So we have VMWare software, which is used to create and run our virtual machines in our entire Cassandra cluster. In our work, 3 virtual machines are created with different IPs. To manage all of them together, MobaXterm is a software which is used for accessing the nodes simultaneously using features like multi-execution mode. CentOS is the operating system, Java JDK 8, Cassandra, and YCSB Benchmark. The setup that is configured for our experiments is shown on this slide. So the first figure shows the cluster of 3 replicated nodes. And the second figure shows the execution of node tool status command. It shows that the nodes are connected and are in the same cluster. and the IPs of the nodes are mentioned. For our experiment 1, the aim is to identify a methodology for benchmarking the performance of Cassandra and to show how different settings affect the performance. So the setup of our experiment is that, as already mentioned, we have a cluster of 3 nodes that are connected. The replication factor is set to 3, which means that all the 3 nodes have the data which is loaded. A key space is created named YCSB and it has a table called user table. Now the table has to be loaded with data. So for that, YCSB benchmark is used and it provides a range of workloads. Workload C is used for read operations and workload A is used for write operations. Here we are analyzing 2 different scenarios with read and write operations separately. A series of YCSB read-write performance workloads are loaded and executed in the cluster, which is 3 replicated. 25,000 records are used for performing the operation. The results are calculated by considering a range of threads from 10 to 1000. And for 3 different consistency settings, the results are measured. So here the table show the latency and throughput measurements obtained. Table 1 denotes read operation measurement and table 2 denotes the write operations. It can be seen that one consistency setting has the lowest latency. Because it has less work to do, it has to get validation from only one node from the cluster. So it has lower latency and all has higher latency. For simpler understanding, graphs are extracted from the measured results. The graphs in figure 3 and 4 shows the delay experienced for read-write operations. The x-axis represents the number of threads and y-axis represents the delay. And the 3 lines denote the latency for one quorum and all consistency settings. The average latency for all is highest compared with one and quorum, is already mentioned because it has to get validation from all the nodes in the cluster, which increases the latency. And for one consistency, it is seen to give the lowest latency, but sometimes it overlaps with quorum. Similarly, there are throughput graphs. Here we can see that the throughput for all is the lowest because it has to take validation from all nodes and it can reduce the execution speed, resulting in low number of operations per second. Now for experiment 2, we want to evaluate the performance using mixed of read-write workload. And we want to narrow down the options for consistency settings based on the performance. And to perform predictive analysis is an aim for this experiment. In a 3 replicated system that you are working on, there are 6 different consistency settings that can be considered, which provides high data consistency. Out of all the combinations, the first 3 settings can provide strong consistency. The first 3 combinations are taken into consideration for this experiment. And as discussed earlier, the equation where the nodes read plus written has to be greater than the replication factor. So the first 3 combinations agree with that equation and they provide strong consistency. Here, mix of read-write operation are considered, such as 1090, which means that there are 5 different workloads considered, such as 1090, which means that 10% are the read operations and 90% are write operations. And similarly, results are extracted for all the combinations. Here, the workload considered has 10% read operations and 90 write in the table 4. 3 different consistency settings are considered as mentioned, which is 1 read, 3 write, 2 read, 2 write, 3 read, 1 write. And threads are from 10 to 1000. And latencies is measured for each combination. The 1 read, 3 write configuration delivers the lowest latency up to 200 threads. And after that, 3 write and 1 read shows optimal performance. Table 5 and 6 show the results for workload read 30, write 70, and read 50, write 50. Here it can be seen that the 1 read 3 write setting provides the best results. And for table 7 and 8, where the workloads are 70 read, 30 write, and 90 read, 10 write, we can see that when the number of threads increases, the 2 read, 2 write provides better consistency. So from all these results, we can observe that regardless of the current workload, the 1 read 3 write consistency setting delivers the best performance. And as the number of requests per second increase, the fraction of read request increases. The 2 read and 2 write, 3 read and 1 write becomes less useful, as in when the load of write operations increases. Also, Cassandra has fast write, so we can support that statement with our experiment. And here we have narrowed down the 6 settings from 3 to 1. Quickly going through the multiple regression equations. So here we can predict the value of y, which is override consistency. We have different independent variables such as read latency, write latency, threads, and proportion of write workload. So using the data that we have generated in our experiments, regression statistics are extracted, and from that we can find an equation using which the write consistency level can be predicted. Here we have predicted the value of read latency. So y, which is a dependent variable, is our read latency, and similarly we have independent variables. If we have the value of the independent variables, then we can extract the read latency for any individual setup. Similarly, we have extracted the equations for predicting write latency. The conclusion. So the work presented here investigates the interplay between different consistency settings and performance of the Cassandra NoSQL database. Through the experiments, a way to find the optimal setting is described such that it results in good performance. And also we have extracted some regression equations from the data using which the developers can predict the values for consistency, latencies, and throughput for their unique setup. For the future work, we can increase the number of nodes that are used in the experiment, and that will expand our data sets. The setup can be deployed on a larger scale, such as a cloud service like AWS, and options for consistency can be increased when the number of nodes will increase. Here are some of the references that I have used for my research. Thank you all for listening.